Hey everyone and welcome. Today we are diving into one of the biggest, most important ideas in all of science, the mole. Seriously, if you want to speak the language of chemistry, you have to understand this concept. It's what lets us connect the tiny, invisible world of atoms to the amounts we can actually see and measure in a lab.
I mean, that's the fundamental problem, right? As a chemist, you're working with atoms and molecules, but they are just impossibly small. There are billions upon billions of them in the tiniest speck. You can't exactly put one on a scale and count 1, 2, 3. So chemists needed a shortcut, a better way, a single word for a gigantic number of particles.
Think of it just like this. When a baker says a dozen eggs, you instantly know they mean 12. It's just a handy way to talk about a specific number. While the mole is the exact same idea for chemists, but on an absolutely massive scale. It's the chemist's dozen. But instead of 12, it stands for a mind-boggling number, 6.022 times 10 to the 23rd power.
Okay, so let's make it official. 1 mole, which we usually symbolize with a little n, is this fixed number of particles, Avogadro's number. And it doesn't matter what we're talking about. Atoms of gold, molecules of water, whatever. 1 mole of anything is always that same huge quantity. Getting this number down is the key to, well, everything else we're about to talk about.
And here's why this is so important. The mole is our central hub. I want you to think of it like a universal translator. It allows us to build these bridges from that invisible world of particles to things we can actually measure, like how much something weighs or the space it takes up. So let's head across our first bridge.
So, let's cross this first bridge, which is probably the most important one you'll use. Knowing the count of particles is great, but in a real lab we use scales. So the real-world question becomes, what does 1 mole of something actually weigh?
And the answer to that question is something called molar mass. It's pretty much exactly what it sounds like. It's the mass of 1 mole. You just look at the periodic table, add up the atomic masses for your molecule, and that's it. So for water, H2O, 1 mole of it weighs about 18 grams. So we say its molar mass is 18 grams per mole. See? Simple as that.
Okay, so here's where the rubber meets the road, and trust me, you'll see questions like this on every exam. If you've got a certain mass of something, say 9 grams of water, you just divide that by its molar mass, so 9 divided by 18, that tells us we have exactly half a mole of water. Easy.
All right, so we've successfully crossed the bridge from a mass we can weigh to the number of moles. Now, let's build our second bridge. How do we get from our central hub, the mole, back to the actual individual count of all those tiny particles? This is where our old friend Avogadro's number comes back into play.
And you know what? This one is super straightforward. It's a simple two-way street. If you have the moles and you want to find the number of particles, you just multiply by Avogadro's number. And if you have the number of particles and want to find the moles, you just divide. That's it.
Time for our third and final bridge. Now this one's a little special. It's just for gases. We're not asking about weight anymore. Now we're asking about space. What's the volume that 1 mole of a gas occupies? See, to make sure everyone's playing by the same rules when they measure gases, scientists came up with a standard set of conditions. We call it STP. That's standard temperature and pressure. It just means a specific temperature, 0 degrees Celsius, and a specific pressure. And under these exact conditions, something really cool happens. And this is the amazing part. At STP, 1 mole of any ideal gas, doesn't matter if it's oxygen, helium, anything, it will always take up the exact same amount of space, 22.4 liters. It's this incredible constant. So if you've got a quarter mole of oxygen gas, you just multiply it by 22.4, and you know its volume is 5.6 liters. Done.
All right, so we've got our 3 main bridges built. We can connect moles to mass, particles, and volume. Now it's time to put this powerful tool to work and solve some real chemistry puzzles, like figuring out the formula of a mystery compound.
You know, a lot of the time in a lab, an analysis tells you the percentage of each element in some unknown substance. To find its simplest formula, what we call the empirical formula, you just follow these 4 steps. You pretend you have 100 grams, so the percentages just become grams. Then you convert those grams to moles. And then, here's the trick, you just divide all those mole numbers by whichever one is the smallest. Boom, you get your ratio.
Let's do one together, right now. We've got the percentage breakdown of some unknown compound. Our mission is to use our mole concept to crack the code and figure out the simplest ratio of atoms in its formula.
Okay, let's break it down. Step 1, 40% carbon becomes 40 grams of carbon.
Easy. Step 2, we divide each of those masses by the element's molar mass to get the number of moles. Step 3, we look at our mole values. The smallest one is 3.33, so we divide everything by that. And just like magic, we get a super clean ratio of 1 to 2 to 1. Our empirical formula is CH2O.
The mole is also absolutely critical when you're mixing stuff up in the lab. The most common way to measure concentration is something called molarity, and its definition is just pure mole concept. It's simply the number of moles of something dissolved in 1 liter of a solution. So if a chemist says they have a 1 molar solution, it just means there's exactly 1 mole of that chemical in every single liter. It's the go-to measurement for solutions.
All right, time to level up. Let's kick it up a notch and move into master mode to talk about a concept that's totally vital for understanding what really goes on inside a chemical reaction. We're talking about the limiting reagent.
Think about making sandwiches. If you've got 10 slices of bread but only 1 slice of cheese, that cheese is going to run out first, right? It limits how many sandwiches you can possibly make. It's the exact same thing in chemistry. The reactant that gets completely used up first is the limiting reagent. It's the bottleneck. It decides the absolute maximum amount of stuff you can make.
And finding it? It's actually a really simple 3-step process. First, of course, you convert all your starting materials to moles, back to our central hub. Second, you take the moles of each reactant and divide it by its coefficient. That's the big number in front of it in the balanced equation. And third, whichever one gives you the smallest number, that's it. That's your limiting reactant.
Let's use a super common example, making water from hydrogen and oxygen. The recipe, the balanced equation, tells us we need 2 hydrogens for every 1 oxygen. Okay, so what if we start with 4 moles of hydrogen, but only 1 mole of oxygen? Which one is going to run out first and stop the party?
We just follow the steps. For hydrogen, we take our 4 moles and divide by its coefficient 2, which gives us a value of 2. For oxygen, we take its 1 mole and divide by its coefficient 1, which gives us a value of 1. And since 1 is obviously smaller than 2, oxygen is our winner. Well, loser, I guess, since it's the one that runs out first. That's our limiting reagent.
Okay, before we wrap this up, I want to give you a couple of my favorite exam shortcuts. These are pro tips designed to help you solve problems way faster, especially when you're under pressure in a test.
So remember that empirical formula calculation we did? Sometimes, after you divide by the smallest number, you don't get perfect whole numbers. You might get something weird like 1.5 or 1.33. Well, this little table is your secret weapon. If you see a ratio ending in 0.5, just multiply all your numbers by 2 to make them whole. If you see 0.33, multiply by 3. It's a fantastic trick that saves a ton of guessing.
So let's bring it all home. The mole isn't just some random giant number you have to memorize for a test. It truly is the central translator. It's the most important tool we have for converting between all the different ways we measure stuff. From the mass you can weigh on a scale, to the volume a gas takes up, to the literal number of atoms in a sample, it's really the engine that drives all of quantitative chemistry.
And there you have it. That's the map to the entire world of chemistry. With the mole as your guide, you can navigate between mass, volume, and that vast invisible universe of particles. This concept unlocks the power to answer the most important question in chemistry, not just what happens in a reaction, but how much. You have the key, so the only question left is, what will you unlock with it?